All right, one last remark I want to make about Gauss's law is for a scenario, I want to give you an example that we are not talking about in this class, which is water flow or fluid flow in general. And I just want to point out that Gauss's law, as I mentioned before, is a mathematical theorem that works for any vector field. And since we deal with a lot of different types of vector fields in physics, Gauss's law is very useful in a number of areas in physics. We've already seen it for electric vector fields, magnetic vector fields. It also works for gravitational vector fields, and I want to show you that it also works for something like the flow of water. So if you like, let's imagine that we have a stream and the water is flowing down the stream, and I'm going to represent the flow of water with a bunch of vectors. So each vector is going to be the velocity of the water at that point. And this looks a lot like, you may have seen this for air, for example. If you've ever seen a diagram of a wind tunnel, you see the arrows showing the flow of air around a car or around an airplane. So it's the exact same thing. And everything I say here would work for a wind tunnel as well. So I have this vector field. Now, if I draw a Gaussian surface in the middle of the stream here, maybe like a somewhat spherical surface, I think it's pretty straightforward to see, just schematically, that the amount of water that goes into the surface is equal to the amount of water that comes out of the surface. The amount going in equals the amount coming out, unless there's some sort of a source or sink for water inside the surface. So I didn't draw one, but could we have a source or a sink for water? Sure. A source might be something like a fountain, right? That is a source of the flow field for the water. And a sink might be something like a drain where the water can flow out. And so you can imagine a splash pad. I've been to a lot of splash pads the last few summers now that I have kids. You can imagine a splash pad where I have a fountain here, and over here I have a drain. And so if I draw a Gaussian surface around this fountain, I should expect there to be a net flux of fluid coming through this surface, because this surface contains a source. So I'm applying Gauss's law. If I draw a Gaussian surface that includes the sink, then I would expect a net inward flux through my surface. But if I look in between the two, where the water is flowing from the source to the sink, more or less, it may not be taking a direct route. It may be following the contours of the ground. But if I draw a Gaussian surface over here, then again, all the water that enters the surface also leaves the surface. And so the net flux through the surface is zero, which it must be because that surface contains no sources or sinks. Okay, so Gauss's law is widely applicable in a variety of different problems anytime you have a vector field.